This video I'm going to talk about vector. So this is just a brief introduction of the vector and some of the important properties. So what is a vector? We have studied before what a scalar means. A scalar basically means a number which refer to some of the properties that we talk about. For example, when we talk about the speed, let's see the speed of vehicle, for example, at 20 miles per hour. So this 20 is the scalar. It actually talks about a property for the speed of the vehicle. Or let's say if 70 Fahrenheit, okay, that's related to the temperature, for example. So those are called scalars because we don't have one number over here actually to quantify the property. So vector is different from scalar, which means we need to use a set of numbers with using included we write as a vector in terms of a set of numbers and surrounded by squared brackets. Like for example, if I have a vector of 1, 2, 3, so that's a vector. So which means that we have multiple numbers. The difference between here and the scalar, the two things. First of all, we have a set of numbers, so they're more general. Okay, you can consider this as 120 as just a 20 vector. That's okay. You only have one dimensional. But this is generally you have a multiple entry in a vector. And also this vector has two meanings. It means the size, not only the size, similar to this one, you have 20 and 70 as the size, how fast, for example, how high the temperature. This one has a size, but also it has a direction. So that's the difference between the scalar and the vector. So this vector you can consider as a set of numbers put in the square bracket to represent magnitude and direction. For example, if I do right over here, if I want to represent x, y, z, let's say here I have vector is 1, 2, 3, and along the x direction it has 1, so it's the 1. Okay, put a 1, and for the y it has 2, and for the z it has 3. So if I do this one, I can actually draw a vector. If I consider this 1, 2, 3, like 1, 2, 3 as a coordinate in the x, y, z domain. So I can find the point, assuming I'm starting from 0. And 1, 2, 3 is my ending point. If I find the ending point to be here, so I can draw a vector starting from 0, 0, 0 to this point, which is represented by 1, 2, 3. So you sort of consider this is a vector we're talking about this. Okay, this is a vector starting from 0, 0, ending at whatever number we have in the vector. That will represent the vector. So one thing is kind of interesting is you can actually shift the vector to the left and right, up and down, front and behind. Doesn't matter if you shift or not, because it's always the same vector, which means it has the same length, or we call it magnitude, and also it has same angle. It points to the same direction. So as long as we have same magnitude in the same direction, the vector will be the same. So you can have multiple vectors like this. For example, I have another vector which is another shift along this direction. For example, I'm going to shift over here. So this will still be 1, 2, 3 because we just shifted this one by along the z-axis, so it doesn't change anything. It's the same vector, still 1, 2, 3. Okay, to summarize, so the vector just means the magnitude and the direction that we're talking about. So it's not just magnitude we mentioned for the scalar, for example. Okay, so since we're talking about that the vector represents both magnitude and other direction, we want to see how do I calculate the magnitude of vector. Okay. Okay, so this is a general situation. So let's say we have a vector which is n-dimensional. I call it nd vector. We have n entries in this vector with a1, a2 until an. So we have n entries in this vector. So this is, like you can see, this is a 3D vector. 3D vector. So this is nd vector. So the magnitude is given by the square root of the square of each entry, and you put the sum, which means have a1 squared, a2 squared until an squared, and then take a square root. That's my magnitude. So for example, if I have this vector is 1, 2, 3, so its magnitude is given by the square root of 1 squared plus 2 squared plus 3 squared, which is square root of 1 plus 4 plus 9, which is square root of 14. That's my magnitude. Okay. And this is the notation wise, I use the two vertical bars just around this vector to represent the magnitude. That's the notation of the magnitude of the vector. The second question, since I also represent direction, I want to say, well, how do I find directional vector? So directional vector is just you normalize the vector, okay? It's a unit vector of the original vector. It's called is represent direction. So it is so notation wise, it's given by a kind of upside down kind of hat, a hat, that because it's still vector, so it's a vector. So I want to emphasize here. So when we say vector, we use this notation to represent this is a vector. Okay, if you only say a, so typically means a scalar. Okay, so since it's here for the unit vector, it's still vector. So a hat vector. This is a unit vector. Okay, this is direction of a in terms of notation, which is computational wise is given by a vector itself divided by the magnitude. So the magnitude is computed right over here. Okay, right over here. Okay. Okay, that's where we compute the direction. Okay. For example, if I give you a vector a which is 1 1, so the unit vector a hat is given by 1 1 divided by its magnitude, which is given by this 1 1 vector divided by square root of 1 squared plus 1 squared, which is 1 1 divided by square root of 2. So if I would draw it over here, let's say I'm going to say I draw the vector a vector right over here. Okay, my a vector, this is my x, this is y. So I mentioned here the vector of a, you can represent a vector as you're starting from 0 0, you're ending at a point represented by this vector, which is 1 1. Okay, which means along the axis it is 1. Okay, y-axis is also 1, so this is my point. So the vector itself is over here. So that's the original a vector. So this is unit vector is you divide by square root of 2, which means, oh, I make it unit length. So this is the length of this guy, the magnitude of this guy is square root of 1 squared plus 1 squared, right? Which is square root of 2. So it's more than 1. So you actually scaled it back. So a hat, the unit vector is sort of you scale it back a little bit to make sure this length is equal to 1. Then you have the unit, the direction of a. Okay. So if we are talking about 3D space, which means we have 3 entries for this a vector, so we have a number of special unit vectors. So we call the unit vectors along x-axis, the unit vector along y-axis, and unit vector along x-axis. If you draw it over here, so unit vector along x-axis, you just pick as a unit vector is 1. Basically, you have 1 0 0 over here. Okay, let's use a blue color. So this is 1 0 0. Okay, this vector is 0 1 0. Let's use the red one. 0 1 0, and my unit vector along z-axis is 0 0 0 0 1. Okay, so that's my unit vector along x-axis, y-axis, z-axis. This is my what I mean physically. Okay. Okay. So that's the basic property we want you to be aware of the definition of vector and also how to compute the magnitude as well as the direction. Okay. Now let's move to the vector operations. Okay. So vector operations kind of similar to the scalar one. So if I have scalar a, let's say a and b, for example, I can have a plus minus b and a times b and a divided b, something like that. It may not apply all to the vector operation, but some of them still apply to vector operation. So I'm going to talk about some of the properties in the next few minutes. Okay. So the first of all is vector additions, and also you can say a vector minus. That's the same thing. So vector addition is you just do the sum of the two vectors. So first of all, if you want to do the addition, we must be able to have the same sign in terms of vector. For example, this is ND. This must also be ND. So that must match. Otherwise, we cannot do the addition. So the operation is pretty similar. We just do it entry-wise product sum. So we just have it. Okay. For example, if A is 1 0, B is 0 1, so A plus B is just to do entry-wise sum, and you put it as a new vector. Okay. This is mathematically how we compute that. The physical meaning of the vector addition is you actually kind of trying to do some kind of operation of the two vectors. So let's say, assuming that my A vector, B vector, we actually can draw a vector over here. For example, if I have x, o, y, x, y. So if I draw A vector, so A vector is you start from 0, 0. Your ending point is 1, 0, right? So our ending point is 1, 0. So which is this point? This is 1, 0. So I can draw my vector right over here. This is my A vector. Similarly, B vector is we're starting from 0, 0 again. Ending is 0, 1. Ending is 0, 1, which is this point. So I can draw my vector over here. So A plus B is you can keep A. You still starting from 0, 0, and you keep A, for example, over here. You just need to shift your B such that your beginning of your B is the ending of A, which means I'm going to shift my B right over here. So it's going to shift your B vector from the 0, 0 to the ending point of AA. Then you get an ending point of this B, new ending point of B. So this point, you start from 0, 0, and then you draw the point from the 0, 0 to this new ending point for B after you move B vector. By letting the starting point of B vector be the ending point of A vector. Now you get this A plus B. This new vector is A plus B. Okay. So this is what I summarized here. So A and B vector is the sum is you make the ending point and the starting point of B to be the starting point of B to be the ending point of A. Then the starting point of A and the new ending point of B will form the new vector of A plus B. Okay, so the second one probably is called the multiplication of a vector by a scalar. So you can multiply a vector by a scalar. Okay, for example, if I give you a vector A, which is A1, A2, A3, and I give you a scalar, this is a scalar, okay, scalar, which means it could be 1, 0.1, it could be 10, whatever value we have. So this C times A is you do entry-wise product of the value of the original value by this C. Now you get the matrix product. The vector product by multiply the vector by a scalar. For example, if I do A1, A vector is 1, 1. If C is 2 and C times A is just you do 2 times each entry, so you get 2, 2. If C is -1, you have C times each entry, -1 times each entry, you get -1, -1. If C is 0, you get 0, 0, 0. Okay, so if I represent over here, for example, if I have A, okay, vector, it's A vector original itself is 1, 1, okay. I started from 0, 0, my ending point is 1, 1, okay. So this is my vector. So if C is 2, you basically doesn't change the direction of A, but you multiply, you make the length to be twice original A vector. If you C is -1, you just change the direction to be the opposite, and then you actually do you actually don't change the magnitude. If C is 0, you just get 0, okay. Which means the scalar typically, if a scalar is positive, if C is positive, which means we just don't change the direction of the C of A has the same direction as A, and then you just make it longer or smaller, okay. If C is negative, use the opposite direction as A, and then you make it the length to be smaller or bigger depending on the absolute value of C, okay. The next one is the product of vectors. So when we talk products, we're actually talking about two types of products. One is dot product. It's different from the A times B in the fourth scalar. There's no different, just one way to define it, okay. The product for vectors have two different ways of computing that. One is dot product, one is cross product. The dot product of A cross B will return a scalar, which means if I do A dot B, this gives me a scalar, okay. And also A and B must have the same size, which means if A is ND, so B must be ND. They have the same size, okay. The cross product is different, so A cross B will return a vector, okay. And also A and B must be, I've emphasized here, must be 3D vectors, which means A must be A1, A2, A3, B must be, you cannot have lower dimension or high dimension. It only applies to the 3D for the cross product, okay. Okay, let's begin with what is dot product. how do you find dot? Dot product actually defined by this. It's pretty straightforward. So A dot B is you do entry-wise product, and then you do the sum. Okay, this is how we compute that. For example, if I want to give, let me see if we get example later on. Okay, don't have example. Let's do it over here. For example, you have an A which is 1, 1. Okay, B is 0, 2, for example. So A dot B is just you do entry type, so 1 times 0 plus 1 times 2. So this guy give us 2. That's it. Okay. So this is how we compute that. It's pretty straightforward. Another way we can interpret the physical meaning of the dot product is A dot B is equal to A magnitude. So I already talked about how to compute the magnitude at the very beginning, right over here. Okay. So the magnitude is A magnitude times B magnitude times the cosine of gamma. This is gamma is between 0 and 180 is the angle between A and B. So I draw a picture over here. So the A over here, B is vector over here. So this gamma is the angle between A and B. Whatever is should be less than 180. So even if you change your gamma, if I change the gamma to be here, let's see, right over here, as the B vector is over here. So this is my new gamma. Okay, it should be less than 180. Okay, so which means this cosine started between 0 and 180. Okay. So in other words, if alpha is pi over 2, which means they are perpendicular. For example, if A over here, this is A vector, this is B vector, this is pi over 2, for example. I know A dot B will be 0. Doesn't matter, I don't need to know what the A and B, the two vectors are. If they are angle, they're perpendicular, their dot product will be 0. Okay. So sum the product for the dot product. So A dot B is also B dot A, which is straightforward because you do entry-wise product. Doesn't matter if you switch it out or not. Also, A plus B dot C is equal to A dot C plus B dot C. Okay. The third one is A dot A is A magnitude squared. This is pretty straightforward because A times A, according to the physical meaning, which is is A dot A, which according to here is the meaning is A negative times A magnitude, because that's the same time cosine gamma. So the two vectors, they're the same. The gamma is 0, right? Because they're actually on top of each other. Okay, so gamma is 0. So cosine 0 is 1. So I have A now squared. Time cosine is 1. So that's why it's true. Okay, so I want to talk lastly. I want to talk about the sum application. Why we want to study dot product. Okay, the dot product is pretty useful when we talk about some real application. For example, if I want to project a vector A onto another project B, for example, hey, if I would project my A onto another vector B, for example, I want to calculate what is the vector C looks like. Okay, how can I compute that? So you can actually use the dot product to compute that. So here's how we compute that. Let's see which is the C is a vector. That is, we project A vector onto the B vector. So if I look at this picture, I can see that. So first of all, the length of C is the length of A times cosine gamma. Okay, so here is what I'm trying to do over here is, first of all, I'm going to know this is the length. This is the length of C. The length of the new vector C is the projection of the length of A onto this B, which means is the length of A. Length of A is the norm of A times cosine gamma. That's the length of C, right? But of course, this is not this is only length. This is only scalar. It's not a vector. But I want to know the vector of C, right? So what I need to do is I need to times the unit vector, because this is the length. I need to times the unit vector to get the C vectors. So this is how to compute unit vector. Unit vector will be B divided by B norm. That's the unit vector of B. If you don't remember, this is also we call it direction of B, which means the C is equal to the direction of B, which is unit vector of B times its length, right? Now what I can do is, I can do B norm, B magnet, B vector divided by, I can multiply the B over here, B norm over here and magnitude, and also multiply B magnitude. The reason I do that because this one will be equal to A dot B. Okay, so this one will B norm, is B vector divided by B norm, B magnitude times B vector will be B magnitude squared, and this becomes B magnitude times A magnitude times cosine gamma. If I look at this, A times B times cosine gamma, which is just dot product, right? Which means, hey, I have here is B vector divided by B vector magnitude squared times A dot B. So this is dot product. So I can use dot product actually an original vector. By calculating this magnitude squared, I can compute the projection of A onto B. Okay, that's kind of the one example about the application of dot product.